Hello and welcome to 15-Minute Math. So today we're going to talk about kind of an oddball with regards to our power rule for antiderivatives, or you might call it the inverse power rule, or whatever your name for it is. But what we're going to try to find is the antiderivative of 1 over x, but that's sort of an outcast when it comes to this power rule. And so I've got this written in black, how to use this power rule. So if I'm taking the antiderivative, I'm trying to find the antiderivative, 1 over x to the n dx. That's our rule that gives it to us. And let's see an example. It's always good to have a nice numerical example. So let's say we're going to find the antiderivative 1 over x cubed dx. So how I would really want to write this so I can use my power rule is x to the negative 3 dx. And now I can use my power rule like normal, so I'll add 1 to my exponent, which would give me x to the negative 2, and then I divide through by that new exponent. And don't forget your plus c. Now, of course, this is kind of a goofy way to write that. So, in fact, it's going to be 1 over 2, we'll make that negative 1 over 2, times 1 over x to the 2 plus c. I just realized I forgot a negative sign in this little rule here. Zzz, there we go. And let's make sure this actually works. In our case, n was 3, which means n minus 1 is 2, and you can kind of see that's going to exactly match the general template that we see right here. So that's kind of our general template. And of course, you don't have to write it. You don't have to separate your factors like that. You could write it as 1 over 2 x squared plus c like so. And that's good for all the powers of x until you get to 1. This really presents a problem for x, or for n being 1. So let's see why that is. Let n equals 1, and then we're going to find the antiderivative of 1 over x, or x to the 1 for emphasis. And let's apply our rule. That's going to be negative 1 over 1 minus 1 times 1 over x to the 1 minus 1 plus c, which is negative 1 over 0. And there's our problem. That's 1 over x to the 0 plus c. But that first factor is a problem, right? We can't divide by 0. And so this whole expression is going to be undefined. So this rule does not work to find this antiderivative. So we're going to have to come up with another way to find the antiderivative of this function, 1 over x. And, kind of in the vein of this playlist, we're not going to necessarily rigorously prove it, but hopefully I can provide some justification for you for why the antiderivative is what we chose it to be. Now, let's remember from the fundamental theorem of calculus, if I want to find the antiderivative, that's the same as finding an integral. Or another way to say that, if I want to find the integral of a function, I can just find the antiderivative and then plug in the endpoints. Let me clarify what I mean. If I want to find, let's say, the integral from 3 to 1 of 1/3 x squared dx, I can just find the antiderivative of 1/3 x squared, which using my power rule should just be x cubed, and evaluate that from 3 to 1, which is to say I'm going to plug in 3 to my function and then plug in, whoops-a-daisy, plug in 1, and there we have it. It's 27 minus 126. But the key to that was we just utilized the antiderivative of our original integrand. And so what we're going to do is we're just going to kind of experimentally try to find the antiderivative by looking at a definite integral and then seeing if we can find a function that matches that area under the curve. Okay, remember, whenever I'm finding an integral, all I'm doing is finding the area under the curve. For that little function there, it's a squared function, but it's kind of been flattened a little bit. So it's going to look something like that. Yikes, wasn't very good. And then I'd be finding the area between 3 and 1, so it's kind of like maybe that area in there, right? Maybe that's 1 and that's 3. I'm looking for areas when I'm finding integrals. So let's go over to Desmos. You can see I've got 1 over x is my function here. Let me turn off my inequalities. 1 over x is this function, and all we're going to do is we're going to find the area under this curve from 1 to a, from 1 to some number. Let's see here. Let's start off with a being positive. Oh my gosh, I don't have that. There we go. And what we should notice is if, let's say I'm going from 1 to 2, well, that's exactly the area under there. Notice this integral is what's giving me the area, is exactly the same as the natural log of that number, right? If a is 2, the natural log of a, which would be natural log of 2, gives me the same output as the area. If I take it over to 3, natural log mirrors it again. If I take it over to 4, same deal. The natural log of this a always gives me the area under that curve. And remember by the fundamental theorem of calculus that if we can find the area, a function that gives us the area under the curve, then we have found the antiderivative of that function. So what this is implying to us, let's go back to our whiteboard. I want to find the antiderivative of 1 over x. That should just be the natural log of x. Well, plus. Because this natural log is always giving us the correct values for the areas under the curve. So like I said, this is not by no means a rigorous proof of the fact, but hopefully it is convincing for you. And some people might be saying, okay, sure, if we go from 1 outwards on, to the positive side, it works, but what if we would go to the negative side? And it still works. So let's say we went from 0.5 to 1, I get a negative 0.693. Well, look at the natural log. The natural log of 0.5 gives me negative 0.63, which should make some sense, right? Because if I'm taking the natural log of some number less than 1, I'm going to be getting a negative result. Also, don't forget a little ticky-tack thing about integrals. Since 0.5 is less than 1, basically what this is telling us is, obviously this is a positive area, but since we're kind of going backwards in our bounds of integration, it's going to be a negative number. So we're still getting the right results. Okay. Now, someone else might be saying, okay, well, sure, in quadrants 1 and 4, this at least experimentally seems to work. What happens in quadrants 2 and quadrants 3? Well, that'll still work. Let me turn off these inequalities, turn on this inequality. So now if I go from, let's say, negative 1 to a, I have a problem. Notice that, well, you can't feed negative numbers into a natural log. So our rule doesn't quite work. But what happens if we use negative a? Now notice we agree again. So what's the trick here? If a is negative, well, that's kind of a problem, but not really. We just use a negative sign inside our natural log. So actually what I wrote on my whiteboard is not quite the truth of the matter. We don't want it just to be the natural log of x, because that does not necessarily work to give us the right areas if we're on the left half of the coordinate plane. So actually what we should say is the natural log of the absolute value of x. And that gets us exactly where we need to go. And another thing to think about is when we're finding antiderivatives, the domain of the antiderivative should pretty much match the domain of the original function. And 1 over x has a domain, well, remember 1 over x, well, it's the hyperbola we saw on the screen here. So we can see it goes from negative infinity to 0 and then 0 to infinity. What about the domain of the natural log of x? inputs? Well, if we're not using the absolute values, the domain of the natural log of x is just 0 to infinity. So in order to match my domains, if I instead use absolute values, now all of my negative numbers, well, all my negative inputs are going to become positive, and then now I can add on this part of the number line. So if you want to think about this absolute value being necessary from our experimental perspective, that's a good way to think about it. Or you can just think about it, I need my domains to match, and that's the way I can get my domains to match. So that's kind of the practical way to think about this. Like I said, I know this is not a rigorous proof. If you're in a proof-based class, this may not cut it for you. But if you're just looking to get some intuition about why this antiderivative turns out to be the way that it is, I think this is a decent way to think about it. So just to recap, the antiderivative of 1 over x is going to be the natural log of the absolute value of x. And let's remember our fundamental theorem of calculus. The antiderivative is like the inverse of the derivative, right? Those are inverse operations. So another way to think about this is to say, okay, well, that also implies that the derivative of the natural log of x, or even the natural log of the absolute value of x, is going to be 1 over x. So there we have it. Maybe I should expand my box. These are probably our two key takeaways from this video. If I want to take the antiderivative of 1 over x, I cannot use that power rule for antiderivatives. I'm just going to have to remember this relationship that the antiderivative of 1 over x is the natural log of the absolute value of x. And we can use the fundamental theorem of calculus to learn one more fact, and that's that if I want to take the derivative of a natural log, the answer is going to be 1 over x. All right, so cutting out the proof saves us a lot of time. We finished with about 3 minutes to spare. In our next video, we'll do some more kind of practical examples using these two facts.